Hey guys, Mr. Backerberg here. In this video, we're going to take a look at piecewise-defined functions. As we're looking at a piecewise-defined function, that's a function that is made up of multiple different functions, each with their own specified domain as to when they get used. So for example, here is a piecewise-defined function. So we've got this function f of x, and it's defined as the opposite of x if the x values are less than 0. So the second piece is the domain for this first definition. Then we've also got x squared if you're dealing with x values that are between 0 and 1, including those end values. And then this function is also defined as 1 if you're dealing with any x value greater than 1. So this function is made up of 3 separate pieces, each with their own domain that tells you when to use each piece of that function. So as we're taking a look at this first example, we're going to be graphing out that piecewise defined function that we just talked about. So let's talk about this first piece where it's negative x for x values that are less than 0. Well, just having negative x, that's going to be a linear function with a slope of negative 1. And there is no b value on the end, so that says that our line would pass directly through the origin. But as we're graphing this out, we only want to graph out the chunk on the left-hand side of the x-axis for all of the x values that are less than 0. We can't technically plug 0 in here because 0 is not included in this domain, but we can get infinitely close to 0. Now I'm going to graph each one of these out in different colors. So this first one I'm going to graph out in red. So what I'm going to do with that is I'm going to put an open circle right at the origin to show that we're approaching 0 infinitely without ever actually getting there. Now this negative x means that we've got a line with a slope of negative 1. So as far as that goes, I'm going to go up and to the left with some points, and this line would extend to the left forever and ever and ever, since that domain is defined for all x values less than 0. So that's going to be the first piece of our function. The second piece I'll draw out in green. So this is x squared. Now we know x squared is a parabola. If we think about plugging in these end values to this function, 0 squared is 0 and 1 squared is 1. These are included, so at 0, 0, that would be a filled-in dot, and at 1, 1, that would be a filled-in dot. Now, because we know that x squared is a parabola, this isn't going to be a nice straight line, but it's going to have a parabolic curve to it as we're graphing it out. And then for this last piece, I'll graph this one out in blue. This function is just defined as 1 for all x values that are greater than 1. So when you've got a constant, that's a flat horizontal line through that specific y value for all x values that are greater than 1. So we're going to have an open dot there since we can't truly plug in 1, but we can infinitely approach it. And it's a flat horizontal line along 1 extending to the right forever and ever and ever, since this is defined for all x values that are greater than 1. Now, as we're taking a look at this example, we're given a picture of a graph to look at, and we want to try to write out a piecewise defined function for what we're seeing in the picture. Okay, so we're going to have some function f of x that we're writing out, and this function is going to be made up of 2 separate pieces since there's 2 pieces to our graph. Now let's just look at that first one. This first piece looks like a line. If we look at its slope from start to finish, it goes up 2 over 2. So it looks like a line with a slope of 1. So that's just going to be x. And it looks like it's going directly through the origin. So we don't have to put any plus or minus a constant on the end there. But now we do need to define the domain for which we're using this piece of the function. So for the domain, we're looking at the x values. And this first piece of the graph shows up on x values between 0 and 2. So those are going to be our outer boundary values for that domain. If we look at what's happening at 0, that has a filled-in dot, so that point is going to be included in the domain. But if we look at what's happening at the x value of 2, that's got an open circle, so that x value of 2 is not included in the domain of this first function. Now, as we look at what's happening with this second piece, again, it looks like we've got a line with a slope of 1. So I'm going to start with x. But if we were to trace this back towards the y-axis, continuing that slope of 1, it would hit the y-axis at -2. So I'm going to throw a -2 on the end there. So it's our x graph, but shifted down 2 spaces. Now we do need to define the domain for this piece of the graph as well. So if we look at the x values that are showing up as part of the graph, it's going from 2 to 4. And if we look at 2, there's a closed circle there, so that end value will be included. It wasn't included in the first piece because of that open circle, but it is included in the second piece because of the filled-in circle there. And it looks like we've also got a filled-in circle happening at 4. So we're going to be defined at that point as well. So looking at these two linear chunks of our graph, we can define it as just x for x values from 0, including 0, up to 2, but we're not including 2 there. And for that second piece, that's going to be the function x minus 2 for x values that are between 2 and 4, including each one of those end values. That's going to be it for this video. Thanks for watching.